Professor Sujit, sir. Professor, yes, over to you.
Hi.
Yeah.
Yeah, I'm going to share it my screen.
Yes.
Yeah, hi, good evening, everyone. I'm sorry could not be there in person. I'll be there in 2 days from now. So I'm going to give a small talk on what I've been doing on multi-agent coordination for persisting tasks. So all this started from my PhD work with Professor Ghose and with all the friends around there at that in 2003 to 2006 at IISc. Actually, I was very confused as to what the talk should be like. It should be a synopsis of what we did during PhDs and then extend or do something very recent ones. So I took the later one. So I'll give a very brief outline about what I did at PhD and then do it about a work on persistence task and something on collision avoidance, which we have done recently. So PhD was all about, as Guru Prasad already told, it was all about finding uncertainty, reducing it to as low as possible given an epsilon. So we have like say 3 different regions, and then if I give a multiple agents and you want to fly them to these regions and reduce the information so that it just becomes like as if I know entire area completely. So for that we used 3 different strategies. One was on k shortest path, defining this entire grid as the graph, right? Then I can get a paths that actually tell me which ones are the for every sortie given a flight time, what should be the length of the path, and then which are the areas that I should be revisiting. So the k shortest path gave a kind of a link between the flight time, which was first time introduced into the cooperative search literature. And the second thing is how we can use the graph theoretical methodologies for finding it. But the only catch was that because it's a graph, which means that it is a dynamic, it's just static. So, but as you move, things change, right? So we need to take that into account. So for that, then we used game theoretical approaches. But game theory was relatively computationally heavy. Then we thought, okay, how we can use individual decision making and the information that the each agents have to come up with like a negotiation mechanism wherein they tell which cell each agent is interested in, and if the other agent is able to get better information compared to the current agent, then they'll just release it off. So we use these 3 different mechanisms having different computational overloads. But the fundamental thing is that the approaches that I learned during those time are still useful even now. So there are even a lot of papers that keep popping up with these ideas, and even some of the ideas are still relevant with some of the students who are using it. Yeah. So, okay, so this was with respect to the work within the lab, but the entire atmosphere and a lot of time was between these two, right? Work, but we spent a lot of time on the coffee board discussions, and then each coffee time was somewhere around maybe hour or more than an hour. But really a lot of coffee breaks, and then a play, and then work. So this was the entire lifestyle or the entire time during my PhD, but it was really, really very productive as well as very insightful for me during this time. So using this, so what I'll do now is that I'll just give a brief work on the two problems. Thanks to Rajnikant for bringing up the problem on getting the use of or the issues with cooperative localization into the picture. So this is the entire same problem setup that Rajnikant told. Like you have let's say you have a landmarks and you have an agents that are trying to connect to the landmarks and the positioning. But let's tie that to an example or a scenario or an application where you want to use this system for covering an entire area. So persistently covering an entire area. So that means like it's like a border patrol. You want to continuously monitor it. So in that case, static landmarks are okay? But instead of static landmark, let's say that I use an high-end IMU and then make it more of a moving landmarks, right? So in that case, how can I use these two systems together to come up with some kind of a framework wherein the agents move and find which are the agents, which are the locations that they should go to monitor it. So apart from that, they also have issues like limited sensing, which means that if it is a camera, then it can only see a small part. And then a communication, which is related to how much of distance that they can do. With these three constraints getting in, it is pretty difficult to find any kind of a deterministic strategy for doing a monitoring, because now you need to define, or you need to tell where the localization agents should be there, and also you need to tell where the auxiliary agents should also be there, right? So in that case, like what we thought is, how about we introduce some kind of a learning mechanism so that can we get a better information about it. So the setup is they monitor a given area, minimize the latency between visit of two consecutive visits to the same region. So instead of having a continuous area, so what we thought is, because continuous area is like integrating the entire area to find how much of information is, which are the parts that you have observed. So instead of that, we used a gridded area so that it becomes much easier to look at it. Yeah. So with overlapping, this approach becomes effective. So the idea is to find learning policies for the agents to minimize the collective time to visits between points. So the localization constraints are being popped in two different ways. We assume that there exists localization technique, like let's say we'll pick it up what Rajnikant has developed onto and then we abstract that by saying, if you are connected to two agents, then you are more or less like having observability, which means that they can localize with respect to each other. So we have two different set of vehicles. One is anchor agents and other is the auxiliary agents. Red ones are the anchor agents, and then blue ones are the auxiliary agents, which have a low grade IMU, which can drift very quickly. So having too many is it's very expensive. So that's why we need to have a lower agents also, because the number of agents that you need to cover a larger area is significantly high. So we want to find the policies for the auxiliary agents as well as the anchor agents, such that the entire area coverage is maximized to as much as possible. Yeah? So in a mathematical way, we will use reinforcement learning to solve it. So which means that we need to get some kind of rewards, which is here is, if you don't monitor a region, then you're getting a penalty. So you're accumulating penalty, and your objective is to find a policy by such that you reduce the total penalty of the entire area as much as possible, right? So at each time step, if you don't visit the area, then the penalty keeps accumulating. Yeah. So for this, we developed an algorithm called graph localized PPO that uses a PPO as a baseline for finding the policies. So here we have a minimap, which is nothing but what the agent can sense. And so local map is what the agent can sense. Minimap is a compressed version of the current knowledge of the entire map that the agent has. So these two are the inputs, and then outputs are left, right, up, down, or stay in the same cell for the agent. And this is the proposed architecture wherein you have the agents. All these are connected through a GraphNet, which basically gives an attention to whether I should communicate with the auxiliary, with the anchor agent, or I should be away trying to get some information. And then you connect it through an actor MLP and actor critic framework to get the output. So that gives you your actions. So this is the simulation of an open map wherein you have obstacles with a predefined. So I think if I'm not wrong, it's 7x7 cells by 7 cells is the sensing and the communication range. And you have the star are the anchor agents, and the triangles are your auxiliary agents. And the color is where each map tells you like how much of time is being spent on in trying to visiting between multiple visits to the same area. So if you look at the way in which these agents learn is that you can see that the anchor agents are more or less like in the middle area, while your auxiliary agents, they try to spread across the cross. So other way it could have been learned is like, partitioning the area into small pieces and then trying to come up with a policy for each of the partition areas. But here, because of the presence of these larger obstacles, so I think that idea would not work out, but rather circling, roaming around the entire area, especially with the anchor agent, seems to be a right one. Yeah. So what happens if we increase the percentage? Then obviously the rewards keeps decreasing. After a certain percentage, it almost becomes very very difficult because they need to move across different obstacles, and then trying to learn the entire search space is quite expensive. So in that case, as you can see that the rewards accumulating are getting much reduced, although the amount of percentage time that it is taking is very similar. And we extended that to for different kinds of environments. Let's say that a two-room environment. So in this case, the agent tries to learn that the anchor should be in one, while in the bridge there should be one agent, and the other agent should be inside another room. So here you can see that where the anchor is in the middle, and then other two are on the other two sides. So similarly, if we increase it to 4-room agents, here we can see that 4 agents will take all the 4 rooms, but periodically the anchor agents keep come onto the middle and then try to cover it up to an area so that other agents will not come. And you can see like the entire area is the reddish is where the anchor agents are moving, and then you have the blue lines with the auxiliary agents moving in. So in this way, this is with the performance comparison with random search with communication constraint, and then we have a greedy search with the communication constraints, because if you don't have communication, then the localization is gone. So which means that whatever the information the agent is obtaining is not being accommodated. And then we have a connected least mean square kind of an explosion, and then this is the gallop, wherein we can see that the gallop receives close to much more better than the other approaches. So then we try to see a simple ConOps, if we can work it out. Will it really follow the paths that the anchor and the auxiliary agents are doing? So this is for a 3-agent case, wherein because this was done crazy fly, so all the backend computing was being carried out inside the communication system, and then it was just propagating up the positions to the vehicle. So here you can see that. So most of them are, again, they're, even though it is a 3-agent, they're still roaming around as seems to be a better agent, and every periodically coming onto the center and covering it up. So this is one kind of an application for the cooperative localization perspective that Rajnikant was talking about. And based on this, so it has nice extensions with respect to both the decay rates at which you give to the cells. If the cells having a higher decay rate, then more or less like you tend to be staying there rather than going anywhere else, right? And actually the way in which the decay rates to each of these agents correspond is to very much way in which I did during my PhD, where the uncertainty in a cell has to be reduced. Yeah. So yeah, even after 20 years, still some of the lines are overlapping, but still they are very much relevant to whatever I'm doing even now. Yeah. So other one is this is a very recent one, which now I got excited not because of everything else apart from the name, which is a PANDA, which is a priority-based collision avoidance. So one aspect of nowadays with a lot of work on UAVs and unmanned ATMs coming up. So one is with the logistics and medical UAVs and other types of UAVs that are coming into the urban airspace. So the airspace is expected to be very dense, right? So one way of doing collision avoidance is, as Ashwini and others are working on, using geofence, wherein you want to create virtual roads. Here, what we are trying to do is that we are using the influence or the parallels to what is done in the roads. The main issue here is that in the roads, we have different priority of vehicles, right? You have police vehicles coming with priority. You have ambulances coming with different priority. You have firearms coming at different priorities. So as the priorities come, then the way in which the traffic flow is changing. You typically give way for it, right? So even if it is increased number of UAVs and the presence of heterogeneous vehicles, like you have fixed wing vehicles, you have quads, you have VTOLs, and tomorrow you'll have some other vehicles. So how can we generate paths for heterogeneous vehicles such that you still maintain some kind of a priority, such that these emergency vehicles can move at a faster speed, or somebody kills you, like these vehicles have a emergency suddenly because some kind of failure of its mechanism, or there is a speed issues that it cannot control and they need to be given way, right? So we draw the parallels and then try to see how we can determine a collision avoidance strategies for these vehicles. And the most important thing is that, okay, one thing is, nice thing is that, okay, if I use an MPC kind of a framework that has an optimization built in that really does it well. However, because it's an optimizer, you really don't know within the short time that you want to give the commands, will it be able to solve it within that short time, right? So what we thought is we want to use something more traditional, and then we developed this priority-based collision avoidance algorithm called as PANDA, with deterministic flavor, saying that all vehicles will use some kind of an deterministic way of moving on to the right or moving on only to the left, so that if there is a vehicle that is coming in front, you know that it is going to do a particular way. So you need some kind of a determinism, and especially in collision avoidance. Like even if the ships move on the river or on the sea, they know that they need to follow some kind of a call, right? So if the aircrafts are moving, they need to follow rules of the air, right? Similar to that, we want to use some kind of a deterministic behavior here. And we want to, since we want it to be a computationally efficient, so we will use a potential field-based approach. And we'll try to scale the potential field based on the kind of priority that is being given to the vehicles. So this is what the typical potential field works, wherein you have the full potential that is being applied onto the agent UK is attraction and repulsion, and some functions of attraction and repulsion you have, and this is the force exerted, and then you have the desired velocity. Now what happens is that with the attraction force, but as it goes towards the goal, the attraction force, because the distance is reduced, so the amount of force that is being exerted towards the amount of field that has been exerted towards the goal reduces. So we are just trying to scale it up by putting an additional term over here. And what we want to do is that as you find that agents are closer, the priority plays a role, whether that incoming agent to me is a higher priority vehicle or a lower priority vehicle. If it is a lower priority vehicle, then it should give way to me. While if it is a higher priority vehicle, then I should be given way to it. So that's where we have the priority of PI and PK will play a role in the how much of repulsion force is being exerted. So if it is a higher priority, then its repulsion force is much higher, which means that I get the effect of the repulsion force at much quicker than later into the engagement. So with that, and second thing is that because we are interested in having fields that are not having any kind of a local minimum, so we used a tangential potential fields. So this is how it represents it. Okay? So then, because of this presence of velocity, it could be either a it is attracting you towards the goal or it is repulsing because of the presence of a higher priority vehicle. So we try to give a clipping toward the maximum and the minimum velocity that it can hold. So this is the workflow wherein you predict, this is for each agent, you predict whether a incoming agent is in a collision with you or not. And then you use the prioritized scale force calculation that you have, FFK. And then you do the velocity clipping. And then you just keep on looping with these three again and again to get different trajectories. So this is the effect of priority for, let's say, a simple two vehicles, wherein both of them have the same priority. You can see that they are returning in a nice, like a nice semicircle manner, right? And here you can see that both of them are having same kind of a speed. But if I change my priorities, let's say that blue vehicle to have a priority 3 while one to have a priority 1, is the amount of change that the vehicle 1 is, blue vehicle is doing is much less compared to the vehicle 1, wherein it is trying to give way so that the blue vehicle can go and reach its destination as quickly as possible. And because of this, so you have a bigger velocity changes with respect to the red vehicle. Yeah. So in this way, we can do it for a larger set of agents. Here we have for 12 n is equal to 16. I think this is for 20, and then for 24 we did. So actually, when we were doing, when I was doing this, when I was making those slides for this presentation to show these lines, remembered of what Rajnikant was doing in his MTech, where these kind of agents were moving one across each other by trying to collide or trying to avoid with each other as an entire group. So here is like they can just pass through the group and they'll still have the collision avoidance. So here you can see that priority-wise, with respect to results, where lower priority is ending up with. So if it is without priority, these are the results, right? These are the distances, the completion time. While we can see that with lower priority, there is a higher distance, while with higher priority, you get much smaller distance, which means that they're trying to reach the destinations in a much more straighter manner, a straighter way. And the same thing here. This shows that the no priority has a higher time, while the highest priority has the lowest amount of time. But here is the interesting thing, like between when we give priority, like there is a spacing that occurs between the no priority, the very low priority and the higher priority. So wherein the low priority and higher priority is given has much more spacing so that they can easily go, which means that it also helps us in a safety part of it. And while if it is no priority, then it is somewhere in the middle of this, which is what we expect. So that's what we are doing with a priority-based collision avoidance in terms of vehicles, wherein we want to extend this to one is an additional is the 3-dimension, and other is to see if we can do some kind of field experiments on different vehicles. So because I think that's all I have. Thank you.